So now that we've talked about counting in section 4.4, now we're going to go back to the start of chapter 4 and talk about probability. So this will be 4.1. So in real life, when we talk about the probability of an event, what are we referring to? What are we trying to calculate? Yeah, the chances that an event will actually occur. Okay, so the probability of an event occurring is the chances or likelihood, we'll just say the chances that an event will occur So here I underline a word for emphasis, which is the word will. So this implies that this is a future event that hasn't actually occurred yet. But it's a future event we're trying to find the chances for. So how do you think people go about trying to find the probability of a future event that hasn't occurred? How do you think we can know the probability or the chances that it will occur if it hasn't occurred yet? Yeah, maybe observing past or present events, and then from that maybe we can infer a future or later probability. So this will be categorized under ways we determine probabilities of future events. So the first way is that we're going to observe the past or present to try to determine this future probability. So look at the past slash present. So let's now talk about what needs to be true about the data in the past or present for us to make a good conclusion or inference about the future. Yeah.
Consistent.
Okay, what do you mean by that?
It has to have happened the same way a lot of times in order for us to say that it'll happen again in the future.
Okay, very good. So let me just word that as the past or present we're looking at needs to be representative of the future that we're trying to predict. So the past or present data needs to be representative of the future we're trying to predict. Okay, so let's do an example. So let's say that we're trying to find the probability that somebody from Alaska will become president. And let's say that one way we try to do that is we try to look at the past, look at past data. So let's say that we look at the past presidents, and then we examine whether the past presidents have come from Alaska or not. And then we take the total number of actual presidents who have come from Alaska and divide by the total number of presidents. And that will give us a future probability. So let's see if this is a good way of doing that. So, if you look at all the past presidents, how many do you think have come from Alaska?
0.
Yeah, 0. And then divided by the total number of presidents,
0.
yeah, how many presidents have we had? Yeah, around 46, right? So, so 0 presidents from the past have been from Alaska, divided by 46 presidents from the past. And if we do this, we're gonna get a probability of 0 to say that the likelihood that somebody from Alaska will become president is 0. And every probability is a number between 0 and 1, which establishes a percentage of likelihood. And if we're saying that the probability that somebody from Alaska will become president is 0, that means it's absolutely impossible. 1 would mean it's absolutely certain, and 0 means it's absolutely impossible. So if we're using this past data to make a conclusion about a future probability that somebody from Alaska will be president, and we're saying it's 0, we know that this answer can't be right, because maybe the probability is low, but it's not necessarily 0 or impossible. So what about this past data is leading us to this incorrect conclusion that the probability is 0?
It's never happened before. So
Yeah, but how do you know that the true nature of the situation will also be that it will never happen in the future? Just because it's never happened in the past, does that mean that it also won't happen in the future? Or it could mean that also that it could never happen in the future, but how do you tell that difference?
Because, Alaskan people can still run for election.
Okay. So you know that the answer, because of that, because it's still a possibility that it shouldn't be impossible. But what about this past data is leading us to this incorrect answer?
Not representative.
Okay, very good. So this assumption is not met, which is this past data isn't representative of the future that we're trying to predict. So why isn't it representative? Why isn't this past data representative of this future or present that we're trying to predict?
It doesn't have a president from every state of the United States, so it doesn't consider every single possibility.
there's no like standard for it happening. Is that why?
Okay, so you guys are on the right track. But what we mean by representative is that it should have the same conditions in the past as it does now. So in other words, Alaska is now a state, but in the past, has it always been a state? No. So because of that, just that one thing, it hasn't been representative of the same conditions as now. And not only that, but lots of things in the past have been different politically than they are now. So that's another way of saying that the past hasn't been representative of this future. So because this assumption isn't met, that's why looking at the past in this situation doesn't give us the correct conclusion about this future probability. So this is one assumption. I'll label this under assumptions. What's another assumption you think needs to be true for us to be able to get an accurate conclusion about the future using this past or present data? So if we calculated the probability that somebody from Alaska will become president using this approach of looking at the past and simply counting up the number of people who have come from Alaska, the number of presidents from Alaska, divided by the total number of presidents, what do you think about this calculation is leading us to the wrong answer? Okay, so it turns out that you're dividing by a total number that is only 46. So it turns out that we only have 46 data points because we've had 46 presidents. We need to be having a total number in our data set that is a number that approaches infinity. It needs to be a very large number here that we're observing. We can't just base a conclusion out of 46 things. So the second assumption that needs to be met is that the number of data points that we're looking at in the past or present need to be a number that approaches infinity. So it needs to be a very large number, like a million, a billion, a trillion. It can't just be 46. So past or present data points needs to be a number that approaches infinity. So infinity is just an abstract concept. We don't have an actual number for infinity. We just say that we're approaching infinity. We're getting closer and closer to this abstract large number. Any questions? Okay. So if we're trying to find the probability that somebody from Alaska will become president, we said that looking at the past needs to have these two assumptions. And the way that I just presented to you is by looking at the past 46 presidents, neither of these assumptions are met. And because of that, looking at the past would not be a good way to find this future probability of finding the probability that somebody from Alaska will become president. Because both these assumptions actually fail. And to use the past or present, both the assumptions have to be met. Okay, so that's a counterexample of when you can't look at the past. But let's look at another example. Let's say that you find an arbitrary coin on the street, and you wanted to find what the probability of heads is for that coin. So, can you generate present data on the fly and flip this coin a large number of times, like 1,000,000 times, and basically find the fraction of heads? Would that be a good way to find the probability of heads for this coin? So, what do you say now?
I'd say no, because it's unnecessary.
Okay, good. So it takes a long time to do that, right? But the question right now is, would you get an accurate answer if you were able to do that?
No.
So why not?
Well, I guess it depends on how many times you flip the coin.
Okay, very good. So if you flip the coin a number of times that approaches infinity, meaning 1,000,000 times or 1,000,000,000 times or 1,000,000,000,000 times. So the more you flip it, it turns out that the closer you'll get to the true answer. So in that sense, you're right, it depends on the number of times you flip it, but because we're assuming that it goes towards infinity, then you'll get closer and closer to the true answer, the more that you can flip it. So if you can flip it a large number of times, then this assumption is met. But what about the coin being representative? Would that be true? Yeah, because you're trying to find the probability of heads for this particular coin. So if you flip the same coin, then it'll be the same representative conditions. Now, if you take the same coin and you go to the moon and you flip it, then now it's no longer representative of the same conditions. So if everything is representative of this probability you're trying to find, then this assumption will also be met. So yes, you can find the probability of head for a certain coin if you flip it a very large number of times, because it'll still be the same coin under the same conditions that you're flipping. Any questions? Okay, so yes, you might get an accurate answer for finding the probability of heads by flipping it 1,000,000,000,000 times, but what's the issue of doing that?
Time.
Yeah, it's gonna take way too long to do that, right? So now we're gonna look at another way that people might find probabilities. So this will be mathematical approaches. So one mathematical approach that we'll talk about, among many, is, the first one we'll talk about is called the classical definition of probability. And that says that if you want to find the probability of a desired event, you would take the total number of desired events and you would divide by the number of total events. And just this division, this ratio, will give you the correct probability. So let's go ahead and apply it to the coin example we just talked about. If we wanted to find the probability of heads for a certain coin, let's look at this ratio. Let's do the denominator first. Often that's easier. So for a particular coin, how many total events are possible for each flip?
2.
Yeah, 2, either heads or tails. So we have 2 down here, and then we have the number of desired events. So if we wanted to find the probability of heads, heads would be the desired event. So for each coin flip, how many ways are there to get heads? There's 1. So by this one quick calculation, we can get this answer, which ends up being 1/2. So it turns out that, yes, this is very quick to calculate, but there's a big assumption involved here that needs to be true for you to be able to get an accurate answer. And the assumption is that the number of total events have to be equally likely of occurring. For this coin example, it means that for a coin with the 2 events, heads and tails, for each coin flip, they need to be equally likely, i.e. the coin has to be fair. So here the assumption is all total events must be equally likely. So if the coin is actually fair, then there's an equal chance of heads versus tails on each coin flip. And because of that, then you can use this classical definition of probability, and you can use this ratio and put the number of total events of 2 on the bottom here, and use this ratio of 1/2, and that would represent the probability of heads for a fair coin if heads and tails are equally likely. But if the coin were not fair, then this assumption falls apart, and heads and tails is not equally likely for a coin that is not fair, and you would not be able to just use this ratio and say the probabilities for an unfair coin would be 1/2, because the assumption fails of heads and tails is not equally likely. So, and that makes sense. So you can only use this ratio if the events are equally likely. If these 2 total events are equally likely. Any questions? Okay, so this idea of equally likely, this assumption is really important. So let me illustrate that with this example. Let's say that you have a jar of marbles, and each marble has a certain color and a pattern. Let's say the colors are red and blue, and let's say the patterns are solid or striped. So every marble fits into one of these 4 groups. So let's say that there are 3 marbles that are red and solid, 4 that are blue solid, 5 that are red stripes, and 6 that are blue stripes. So the question is, if you're to reach in and select one random marble, what's the probability that a marble that you select is red and solid? So one way that you could do it is you can do it the first way we talked about, which is to generate present data and perform this experiment a number of times that approaches infinity. And you grab a marble every time you note what it is, and then you repeat this a number of times that approaches infinity, like 1 trillion times. And then you count the proportion of times that you observed a marble that was red and solid. That's one way to do it. But that takes way too long. So let's try this mathematical approach. So if we look at the number of total events here, remember to use this approach. So if we wanted to use this approach, any suggestions on how many total events do we have?
18.
Yeah, so 18 because 18 individual marbles. So that would be, the number of total events here would be 18. And then of those, how many desired events do we have?
3.
It's the one that corresponds to this description of red and solid, which is 3. So the correct answer will be 3 out of 18, or simplified would be 1 out of 6. And this answer is meaningful because it's this exact same answer you would get if you perform this experiment an infinite number of times. If you selected 1 trillion marbles, then 1 out of 6 times you'll end up getting this possibility of a marble that's red and solid. Now, let's say that I play devil's advocate, and I said, well, these marbles that are red and solid, that's essentially this group of marbles here, and there's a total of 4 groups of marbles. So why can't I say that the number of total events here is 4, and of those, there's 1 I desire, which is 1 out of 4. So that's obviously not the correct answer of 1 out of 6, but why, what did I get wrong when I did that?
There isn't an equal amount of marbles in each category.
Yeah, very good. So these number of total events here on the denominator of the fraction need to be equally likely of occurring. So are these 4 group of marbles, are they equally likely of being selected? So no, because this group of marbles with 3 is half as likely of getting selected as this group of marbles with 6. So these are not equally likely, so that's why you cannot put this 4 on the bottom of the fraction here. So this number on the bottom has to be equally likely of occurring. And when we do the 18 here, are these 18 individual marbles equally likely of being selected? Yes, and that's why we were correct in putting the 18 on the bottom of the fraction, because they were equally likely of being selected. Okay, so this assumption is really important for us to be able to use this classical definition of probability. Any questions? Okay, so back to our example of trying to find the probability that somebody from Alaska will be president. So can we say that, okay, I'm going to use this mathematical approach now, and there are 50 states, so we're going to say the number of total events is 50, and Alaska is one of them, so the probability that somebody from Alaska will become president is 1 out of 50. You think that's true? Yeah.
That isn't true because the population of each state is different.
Yeah, very good. So, and that's another way of saying that this assumption isn't met. This assumption fails in this case because this 50 represents the 50 states. And by doing that, we're implying that the 50 states have an equal likelihood that somebody will become president from that state. And we know that that's not true. We know that some states have a better chance of producing somebody who will become president than other states. And because of that, that's why you can't use this approach, this ratio, and put 50 on the bottom of the fraction. Any questions? Okay, so quickly on the time we have left, we talked so far about 2 ways that people find probabilities. One is looking at the past, but in that case, there are 2 strict assumptions that have to be met for that to work. And we also talked about this particular mathematical approach, and that has its own strict assumption that has to be met. And because of that, in real life, oftentimes, we're trying to find probabilities of situations where these assumptions just aren't met. So we're not going to get accurate answers. So because of that, there's a third way that people find probabilities. This is called the subjective approach. And in real life, the word subjective, what does that mean? Subjective as opposed to objective.
It's in the eye of the beholder.
Yeah, good. Subjective is based on opinion versus objective is based on fact. So yeah, subjective is more about what's in the eye of the beholder, what's subject to opinion. So this is just a fancy way of basically saying we don't know, so we're going to use our best guess. So the subjective approach here is basically we're going to use our best guess. So in the example of trying to find the probability that somebody from Alaska will become president, both these approaches we saw had limitations because the assumptions were so strict, and these assumptions were not able to be met on the real life example of trying to find the probability that somebody from Alaska will be president. So because of that, because that has so many variables, maybe the best we can do is weigh all the variables internally and just try to use our best guess. Because we know all the variables are probability that somebody from a state will become president is based on the size of the state, the population, the political influence of that state,
How many candidates?
how well the media likes the state or is biased for or against that state, and what else?
How many candidates?
Yeah, how many candidates from that state are running, and so on and so on and so on. So there are lots of variables, and each variable might have a difference of importance based compared to other variables. So we'll just have to weigh that, weigh each of the variables accordingly. So oftentimes in real life, that's the best you can do, is just use your best guess. And I emphasize this because oftentimes you'll see probabilities of things being reported and thrown at you. And some probabilities that are reported may be accurate if they're based on these two ways and the assumptions are actually met. Some probabilities will be very inaccurate if they're based on just a subjective approach. So now that you know how people determine probabilities, you can think about how those probabilities might have been calculated. So if they're calculated using these ways and the assumptions are met, then they're going to be accurate. But otherwise, they might not be accurate at all. So you have to take that into consideration. So moving forward in the class, we're gonna focus on this approach, the mathematical approach, because first of all, this is a math class, and we're gonna use examples where the assumptions are met, and that'll also train you to try to ask yourself whether future situations have assumptions that are also met mathematically or not. So moving forward, we're going to focus on this mathematical approach to calculation.